A human being can vanish behind a mountain. Earth can vanish inside Jupiter. More than 1 million Earths could fit within the Sun. And the Sun itself would look modest beside a red supergiant. Yet, even those stars are separated by gulfs so wide that light needs years to cross them, and the Milky Way is only one galaxy woven into a universe roughly 93 billion light-years across. That scale can feel unsettling, but it also reveals something extraordinary from one small world. The universe has learned to measure itself. Where are you watching or listening from? And what time is it there? Perhaps it is late at night. Or perhaps this journey is playing while you study, work, or rest. Leave a comment and join the quiet community gathered beneath the same sky. Thank you for spending part of your time here. A gentle like, subscription, or share helps Calm Space Science continue creating thoughtful journeys through the cosmos. The first step outward begins with the smallest object in this story, the human body standing on Earth. A human body occupies so little of Earth that almost every familiar landscape already exceeds it by orders of magnitude. A standing adult may rise less than 2 meters above the ground, while the trunk of a mature redwood can extend higher than a city building, and a single mountain can lift thousands of meters into the atmosphere. Mount Everest reaches nearly 9 kilometers above sea level. Yet even that height is only a thin wrinkle on the planet's surface. If Earth were reduced to the size of a smooth household globe, the greatest mountain ranges would barely disturb its texture. Their apparent immensity comes from the narrow scale of human movement. From muscles that tire on a slope, lungs that struggle in thin air, and eyes that cannot take in an entire continent at once. The mountain feels enormous because the body is local. The planet is not. The same difference becomes even clearer at the edge of the sea. A person standing on a coast sees a horizon only a few kilometers away, curved out of sight by the planet itself. Beyond that narrow visible circle, the ocean continues across distances that no unaided sense can measure. The Pacific stretches so widely that all the continents could almost be arranged within its basin. Yet from a shoreline it presents only waves, weather, and a line of sky. Its greatest depths descend farther below sea level than Everest rises above it. In the Mariana Trench, water presses downward through nearly 11 kilometers, creating a vertical world in which the entire human story would fit inside the uppermost fraction. A diver can enter the ocean, but cannot belong to its full scale. Pressure, darkness, temperature, and distance close around the body long before the ocean reaches its limits. Even a continent, which appears vast on a map and can contain climates, nation, deserts, rivers, and mountain chains, remains only a section of a much larger shell. Human lives unfold on fragments of that shell, so small that most daily movement barely registers at planetary scale. A journey across a city may feel long. A flight across a country may consume hours. A crossing between continents can follow the curvature of Earth for thousands of kilometers. Yet the planet turns beneath all of these journeys without effort, carrying every road, border, building, and coastline through space as a single object. Its circumference is about 40,000 kilometers, a distance so great that even the fastest routine travel still reveals only pieces of the whole. The body measures its surroundings in steps, rooms, streets, and horizon. Earth measures them in hemispheres. This mismatch is not merely visual, it is built into time. A human life may last for several decades, while mountains rise and erode across millions of years. Oceans open and close across tens or hundreds of millions, and continents drift far enough to assemble and break apart over spans that erase almost every direct trace of individual existence. The ground feels permanent because human memory is brief. On geological timescales, the surface is active, mobile, and temporary. Rock folds, bassins sink, ice sheets advance and withdraw. Rivers move their channels. Coastlines migrate. Entire landscapes that once seemed fixed become sediment beneath later worlds. Against that duration, even civilization occupies a narrow interval. Cities appear, expand, and vanish, while tectonic plates continue moving at roughly the speed that fingernails grow. The comparison is gentle but severe. Human beings are not only small beside the height of mountains and the breadth of oceans, they are brief beside the processes that create them. The atmosphere offers another measure. Nearly all human activity occurs within a thin layer close to the surface, where pressure and temperature allow bodies to function. Aircraft climb above weather, but they remain close to the ground when compared with the size of Earth. The atmosphere itself extends gradually outward, becoming thinner until there is no sharp boundary between air and space. Yet most of its mass is concentrated within the lowest few dozen kilometers, seen against the diameter of the planet. This life-supporting envelope is delicate. It is less like a vast roof than a fine film held by gravity around a sphere of rock and metal. Every forest, storm, migration, harvest, and breath depends on conditions inside that film. The scale of Earth makes the atmosphere seem thin, but the scale of a person makes it feel endless. Clouds build far above rooftops. Storm systems span whole regions. Winds cross oceans. Still, all of this weather takes place close to the surface, within a layer that would look almost invisible from far enough away. The body is smaller still, contained inside a shell, contained inside a planet. The comparison becomes sharper when Earth is considered as a volume rather than a surface. Human beings live almost entirely on the outer boundary of a sphere more than 12,000 kilometers across. Beneath the crust lies the mantle, a deep region of hot rock that moves slowly over immense periods. Farther inward, the core begins, with liquid metal surrounding a solid center under pressures beyond ordinary experience. No mine, tunnel, cave, or borehole has come remotely close to reaching the mantle in the way exploration crosses land or sea. The deepest human drilling penetrates only a tiny fraction of the distance to Earth's center. Nearly the entire planet remains physically inaccessible, not because it is distant across the surface, but because it lies below every point of it. Humanity inhabits a boundary, the visible world of soil, water, air, and life is only the exterior of a much larger mass. If the planet were opened in cross-section, the regions familiar to human experience would form a skin so thin that their importance would come not from thickness, but from the extraordinary complexity they contain. That complexity can conceal scale. A single life may include thousands of places, relationships, memories, and decisions. A city can feel inexhaustible. A forest can resist complete exploration. A desert can defeat travel. Each environment contains enough detail to occupy attention fully, and this fullness creates the impression that the human world is large. In one sense, it is. Experience does not require planetary size to be rich, but physical scale follows a different measure. Every person who has lived could stand within a surprisingly small region if packed closely together. Every building, road, field, and machine occupies only a scattered portion of the land. The structures that seem dominant from the ground remain difficult to detect from orbit unless they form broad patterns. At night, networks of artificial light trace coastlines and cities. but even these luminous marks are thin and uneven against the dark surface. They reveal presence, not magnitude. Earth remains overwhelmingly ocean, rock, ice, desert, forest, and atmosphere. The human layer is active, influential, and increasingly powerful, yet geometrically slight. From the distance of the moon, individual people disappear completely. Cities vanish into color and texture. Borders cease to exist. The planet becomes a bright sphere, partly clouded, with no visible sign of the personal scale that defines life on the ground. From farther away, even the largest storms become details. Continents lose their familiar authority. Earth itself begins to shrink into a point of reflected sunlight. This transformation does not happen because anything changes on the surface. It happens because distance removes the scale that makes human structures visible. A home remains a home. A life remains a life. And an ocean remains an ocean. But the entire arrangement is compressed into a smaller angle of view until difference disappears. That is the first unsettling lesson of cosmic scale. Smallness is not an opinion. It is a relationship between size, distance, and perspective. On the surface, the human body is large enough to hold a mind, cross a valley, build a shelter, and alter an ecosystem. Against a mountain, it becomes fragile. Against an ocean, temporary. Against a continent, nearly invisible. Against Earth as a whole, it is below direct detection. Yet Earth, which seems to provide the final frame for all of these comparisons, is not the largest object in its own neighborhood. The planet that reduces every person to a trace will itself become modest when placed beside the giant worlds circling the same sun. Earth seems complete because every human journey, every recorded history, and every known ecosystem unfolds upon it. Yet the planet becomes unexpectedly modest when placed beside the larger worlds that share its star. The first comparison is Jupiter, a planet whose scale changes almost every familiar proportion. Earth is about 12,700 kilometers across. Jupiter is more than 11 times wider, and because volume increases much faster than diameter, more than 1,000 Earth-sized volumes could fit inside it. The exact arrangement would leave empty spaces between the spheres, but the comparison still gives the right physical impression. Jupiter is not simply a larger version of Earth. It is a different class of world, built mainly from hydrogen and helium, deepening through clouds, compressed gas, metallic hydrogen, and an interior that remains difficult to define in ordinary terms. There is no solid surface like the one beneath human feet. A descending craft would not arrive at a landscape. It would pass through layers of increasing pressure and temperature until the surrounding matter behaved less like an atmosphere and more like a dense planetary interior. The size of Jupiter is therefore not the size of a continent enlarged beyond reason. It is the size of an entire gravitational system whose weather can produce storms broader than Earth itself. The Great Red Spot, though variable and gradually changing, has endured for centuries as a vast rotating disturbance. At times, it has been wide enough to contain the whole Earth across its span. From within such a storm, the curvature of the planet would remain beyond any immediate sense. There would be no nearby edge, only cloud bands, winds, pressure, and a horizon belonging to a sphere so large that Earth could disappear inside one atmospheric feature. That comparison becomes more severe when mass is considered. Jupiter contains more than 300 times the mass of Earth. It also holds more mass than all the other planets combined, making it the dominant planetary body of the solar system. Yet its average density is much lower than Earth's, because its material is distributed through vast layers of light elements. This distinction matters. Size alone does not explain a planet. Earth is compact, rocky, and metal-rich, with a thin atmosphere above a hard crust. Jupiter is extended, fluid, and immense, with gravity compressing common cosmic gases into unfamiliar states. The two worlds belong to the same system, but their internal structures are as different as their dimensions. Saturn deepens the contrast in another way. It is slightly smaller than Jupiter, though still almost 10 times wider than Earth, and more than 700 Earth-sized volumes could fit within it. Saturn is less dense than water on average, a fact often used to imagine the planet floating in an impossibly large ocean. The image is physically unrealistic because no ocean could remain stable beneath such a body. But the low density is real and reveals how much of Saturn consists of light material spread through a tremendous volume. Its atmosphere forms pale bands and broad storms, while its interior descends into hydrogen under increasing compression. At the center may lie a dense region of rock, ice, and heavier elements, but even this core is hidden beneath depths that no instrument has directly reached. Saturn's visible surface is only cloud top, a shifting boundary that conceals nearly everything that gives the planet its mass. Around it extends the ring system, wide enough to transform the planet into one of the most recognizable objects in astronomy. The rings are thin compared with their breadth, and are composed mainly of countless particles of ice, rock, and dust. Their apparent solidity is an illusion produced by distance. Seen closely, they are a vast orbital structure, with gaps, waves, moonlets, and particles following separate paths. Earth could fit easily across the main ring system, yet the rings themselves contain surprisingly little mass compared with a planet. Once again, appearance and substance separate. A delicate structure can span enormous distances, while a much smaller sphere can contain far more material. Uranus and Neptune are smaller than Jupiter and Saturn, but they still reduce Earth to a minor scale. Each is roughly 4 times wider than Earth, large enough to contain dozens of Earth-sized volumes. They are often called ice giants because a greater fraction of their interiors is associated with substances such as water, ammonia, and methane under extreme pressure and temperature, rather than being dominated almost entirely by hydrogen and helium. The word ice can be misleading. It does not describe simple frozen layers like a terrestrial glacier. Deep inside these planets, the relevant materials exist in hot, dense, compressed states shaped by conditions unavailable at Earth's surface. Uranus turns with an extreme axial tilt, appearing to roll around the Sun, while Neptune carries some of the fastest winds known in the solar system. Their blue colors, distant orbits, and smaller apparent disks can make them seem calm and remote. But physically, they are enormous worlds with deep atmospheres, powerful weather, and internal structures still only partly understood. Even among planets, Earth is not the middle standard that intuition often assumes. It is the largest of the rocky worlds, bigger than Venus, Mars, and Mercury, but far smaller than every giant planet. This hierarchy reveals how strongly human perception is shaped by familiarity. Earth feels naturally planet-sized because it defines the category from the ground. Its gravity feels normal because human bodies evolved within it. Its atmosphere feels substantial because lungs depend on it. Its oceans feel vast because they obstruct travel. Its continents feel immense because crossing them consumes time. None of those experiences establishes a universal scale. They establish only the scale of one rocky planet. Beside Jupiter, Earth resembles a bead beside a ball. Beside Saturn, it becomes a small object beneath a ring system, stretching far beyond its diameter. Beside Uranus or Neptune, it remains visibly distinct but physically reduced. The comparison can be carried further through gravity. At the cloud tops of Jupiter, gravity is more than twice the strength experienced at Earth's surface, despite the planet's much greater radius. Because so much mass lies beneath, Saturn, though far more massive than Earth, has surface gravity near the top of its clouds that is only modestly stronger than Earth's, a result of its low density and broad size. Uranus has slightly weaker cloud-top gravity than Earth, while Neptune's is somewhat stronger. These values resist the simple assumption that a larger planet must always pull proportionally harder at its visible boundary. Planetary scale depends on the relationship between mass, radius, density, and internal structure. A world may be huge yet diffuse, or smaller yet tightly packed. Earth's own gravity is not a basic cosmic setting. It is one outcome among many. The giant planets also command systems of moons that make them resemble miniature celestial families. Jupiter and Saturn each possess numerous known moons, including bodies large enough to be worlds in their own right. Ganymede, orbiting Jupiter, is larger than Mercury. Titan, circling Saturn, is larger than Earth's moon and carries a thick nitrogen atmosphere over a surface shaped by methane weather. Europa may conceal a global ocean beneath ice. Enceladus releases plumes from a subsurface reservoir near its south pole. These moons complicate the scale comparison because the giant planets are not isolated spheres. They dominate broad regions filled with satellites, rings, magnetic fields, radiation belts, and gravitational interactions. Earth has one large moon and a relatively simple surrounding architecture. Jupiter and Saturn preside over layered systems whose total extent reaches millions of kilometers. A traveler approaching them would encounter not merely a planet, but an environment organized by the planet's gravity. From far away, Earth can still appear visually beautiful and complete, with blue oceans, white clouds, and dark land. Beauty does not alter proportion. The entire atmosphere, biosphere, and crust remain bound to a world that would form only a small spot against Jupiter's disk. Every human being who has lived, every extinct species known from fossils, every forest and desert, every city and ocean, and every event preserved in memory has occurred on that spot. The reduction is not symbolic. It is geometrical. Earth contains the whole known history of life. Yet it occupies only a minor share of the space enclosed by a giant planet. That tension between importance and size will continue through every larger comparison. A world can hold everything that matters to its inhabitants and still be physically small. Yet even Jupiter, the largest planet around the Sun, does not define the upper limit nearby. Its immense body contains only a small fraction of the mass gathered at the center of the solar system. The next comparison does not place Earth beside another planet, but beside the star whose light makes every planetary scale possible. The Sun does not appear large from the ground. It occupies only a small circle in the sky, roughly the same apparent width as the Moon, and its daily movement can make it feel like one bright object among familiar features of the horizon. That appearance is created by distance. The Sun is about 109 times wider than Earth, and the difference in volume is far more extreme. More than 1 million volumes the size of Earth could fit inside it. The comparison is difficult to picture because the mind tends to imagine size through length alone, as though a wider object were simply a larger version of a smaller one. A sphere grows in 3 dimensions at once. When its diameter increases, its volume rises much faster. The Sun is therefore not merely a bigger globe. It is a body so extensive that Earth would occupy only a tiny fraction of its interior. One small world repeated until the count passed beyond 1,000,000. Even then, the total would describe volume, not a practical arrangement of solid planets. Real spheres leave gaps when packed together. So fewer intact Earths could be placed inside without empty space. The deeper point remains unchanged. The star that seems compact in the daylight sky contains room on a scale that almost erases the planet from which it is observed. Its mass sharpens the comparison further. The Sun holds nearly all the mass in the solar system. Every planet, moon, asteroid, comet, ring particle, and grain of dust together contributes only a small remainder. Jupiter is enormous beside Earth. Yet the Sun is about 1,000 times more massive than Jupiter and more than 300,000 times more massive than Earth. The solar system is therefore not a collection of comparable bodies circling a center. It is overwhelmingly the Sun, with everything else moving through the gravitational structure created by its mass. Earth follows an orbit because space around the Sun is shaped by that concentration of matter. The planet's oceans, continents, atmosphere, and every living system upon them travel together around a star whose physical dominance is almost complete. Yet the Sun is not solid. Its immense volume is composed mainly of hydrogen and helium held together by gravity. At the visible surface, called the photosphere, the material is hot enough to glow, but this surface is not a hard boundary. It is the layer from which most visible light escapes into space. Beneath it, matter remains gaseous or plasma-like, with electrons separated from atomic nuclei under high temperature. A body descending into the Sun would not encounter ground. It would pass into increasing heat, pressure, and density, moving through layers where ordinary material could not remain intact. The star's apparent edge is therefore more like a luminous transition than a physical wall. This matters because the Sun's scale is not built from rock, ochan, or metal arranged like a planet. It is built from a deep, self-gravitating fluid, compressed toward a center where conditions become extreme enough to sustain nuclear fusion. In the core, hydrogen nuclei combine through reactions that ultimately form helium and release energy. The process is slow at the level of individual particles, but the core contains so much matter that the total energy production becomes vast. Every second, the Sun converts part of its mass into energy. That energy works outward through layers before finally escaping into space as light and other forms of radiation. The sunlight reaching Earth has crossed about 150 million kilometers in a little more than 8 minutes. Yet the energy that produced it may have spent a very long time moving through the solar interior. The small bright circle in the sky is therefore the visible end of a process occurring inside a sphere of plasma more than 1,000,000 kilometers across. Earth receives only a tiny fraction of the energy that leaves it. Most sunlight spreads into empty space because the planets occupy almost none of the area surrounding the star. Earth intercepts enough to drive weather, warm oceans, sustain photosynthesis, and shape nearly every surface environment. But from the Sun's perspective, the planet is a narrow target. This provides another measure of smallness. Earth depends on the Sun almost completely, while the Sun would continue with scarcely any change if Earth were absent. The relationship is physically one-sided. The planet requires the star's light and gravitational stability. The star does not require the planet. From near Earth, that dependence is softened by familiarity. Sunrise feels gentle. Seasons arrive gradually. Warmth spreads through air and water. At stellar scale, The same source is a sphere with a surface temperature of several thousand degrees and a core temperature of many millions. The calm light on the ground is diluted distance. Close to the sun, the environment becomes a domain of radiation, charged particles, magnetic fields, and plasma. Dark sunspots mark regions where magnetic activity alters the flow of heat. Yet many sunspots are larger than Earth. Prominences can arch above the visible surface across distances that would dwarf the planet. Solar flares release bursts of energy, while coronal mass ejections can hurl enormous clouds of magnetized plasma outward through the solar system. When such material reaches Earth, the planet's magnetic field and atmosphere absorb and redirect much of its influence, sometimes producing auroras and sometimes disturbing satellites. Radio systems and electrical infrastructure. A disturbance originating in a region larger than Earth can travel across interplanetary space and interact with the entire planet as though it were one small obstacle in the flow. The Sun's outer atmosphere, the corona, extends far beyond the visible disk. During a total solar eclipse, it appears as a pale structure around the darkened star, with streamers shaped by magnetic fields. From this outer atmosphere comes the solar wind, a stream of charged particles that expands through the planetary system. Earth exists inside that wind, so do all the other planets. The Sun is not merely a distant lamp at the center. Its particles, radiation, and magnetic influence fill the surrounding space, creating a broad domain known as the heliosphere. Earth circles within this stellar environment, much as a small boat might move inside a current too large to perceive from its deck. At the Sun's visible surface, gravity is almost 30 times stronger than at Earth's surface. Yet the Sun's size is so great that an observer near its outer layers would not see the entire star as a neat sphere in the way it appears from Earth. The horizon would curve gently across an immense luminous expanse. Regions separated by distances greater than the width of Earth would form only local features. The idea of standing there is physically impossible, but the imagined perspective helps reveal how thoroughly planetary intuition fails. What seems like one object from far away becomes an environment when approached. Earth can be crossed, mapped, orbited, and photographed as a whole. The Sun is large enough that even its visible surface contains patterns operating on scales comparable to planets. Granules, formed by convection, cover the photosphere, each a shifting cell of rising and sinking plasma. Beneath the surface, energy moves through layers whose depths would contain Earth many times over. The planet that feels like a complete world becomes only a useful unit of comparison inside the star. Even the distance from Earth to the Moon, so vast by human standards, would fit within the Sun's diameter several times. The entire Earth and Moon system could pass across the solar disk and still appear small. This is why accurate models of the solar system are difficult to build at ordinary scales. If Earth were represented by a small bead, the Sun would have to be a large sphere placed far away, and the planets between would be reduced to scattered points. Models often enlarge the worlds or compress the distances so they can fit into a room, a page, or a screen. The result helps identify objects, but weakens the physical relationship among them. In reality, the Sun is both huge and distant, while Earth is both small and separated from it by an enormous gap. Holding both truths at once is difficult. The star's diameter can swallow more than 100 Earths in a straight line. Yet, the space between Earth and the Sun could contain that diameter many times over. Scale continues outward in layers, each one correcting the impression created by the one before it. The Sun, therefore, marks the first truly overwhelming object in the sequence. Mountains reduce the human body. Earth reduces mountains. Giant planets reduce Earth. Then, the Sun gathers almost the entire mass of the solar system into one luminous sphere and turns every planet, including Jupiter, into a minor companion. From the surface of Earth, the Sun looks manageable because distance has compressed it into a bright disk. In physical terms, it is the dominant structure of the local system, the source of nearly all its light, the anchor of its orbits, and the engine behind the climate of the only inhabited world known. Yet this apparent summit of size will not remain secure. The Sun is immense beside Earth, but stars are not built to a single scale. And beyond, the familiar yellow disk lie stellar bodies, whose dimensions make even the center of the solar system look restrained. The Sun becomes less exceptional as soon as it is placed among the full range of stars. It is a stable main-sequence star, a sphere of hydrogen and helium whose core has been fusing hydrogen for billions of years. And in many ways, it is well suited to long-lived planetary systems. But size alone does not make it remarkable. Across the Milky Way, stars form with different masses, evolve at different rates, and expand into very different final shapes. Some remain smaller and cooler than the Sun for spans far longer than the present age of the universe. Others begin with so much mass that they burn through their fuel quickly, swell to enormous dimensions, and end after only a few million years. The Sun sits between these extremes. It is neither one of the smallest stars nor remotely close to the largest. Its apparent dominance comes from proximity. At the distance of Earth, it fills the sky with light and controls the motions of the planets. At interstellar distance, it would become one ordinary point among many. This change in status is not a reduction in physical power. The Sun remains vast enough to contain more than 1 million Earth-sized volumes and massive enough to govern the solar system. What changes is the frame. Stellar comparison replaces planetary comparison, and the object that seemed almost unimaginably large becomes moderate. The first step outward comes from stars only somewhat larger than the Sun. Sirius, the brightest star in Earth's night sky, is larger, hotter, and more luminous, though still not a giant by the most extreme standards. Other stars have several times the Sun's mass and produce hundreds or thousands of times as much light. Their greater mass compresses their cores more strongly, driving fusion at a faster rate. They shine more intensely, but that brightness is purchased with time. A massive star can consume its available fuel rapidly and move through its life in a fraction of the Sun's expected span. Size and longevity do not increase together. The same gravity that builds a more powerful star also pushes it toward a shorter and more unstable existence. As stars age, their dimensions can change more dramatically than their mass alone would suggest. Once hydrogen in the core becomes depleted, the balance between outward pressure and inward gravity shifts. The core contracts and heats, while outer layers expand. A star that spent most of its life in a relatively compact state can become a giant. The Sun itself is expected to follow this path far in the future, swelling into a red giant after its long main sequence phase ends. It may then grow large enough to transform the inner solar system completely. Yet even that future Sun would not approach the dimensions of the greatest red supergiants. Betelgeuse provides a more severe comparison. It is a red supergiant in the constellation Orion, a massive star in a late stage of evolution, with an extended outer atmosphere and a radius hundreds of times greater than the Sun's. Its exact boundary is difficult to define because the outer layers are diffuse, variable, and surrounded by material expelled into space. A rocky planet has a clear surface. A red supergiant fades outward through moving gas, giant convective cells, dust, and changing opacity. Any stated radius, therefore, depends partly on how the star is measured. Even with that uncertainty, the scale remains immense. If Betelgeuse were placed at the center of the solar system, its visible layers would extend far beyond Earth's orbit and perhaps toward the region occupied by the outer inner planets, depending on the measurement used. The Sun, which dominates every familiar planetary comparison, would fit inside Betelgeuse, not as a rival, but as a small central sphere. The volume difference would rise into hundreds of millions of suns if simple spherical estimates were applied, though the changing, uneven atmosphere makes such comparisons only approximate. The physical experience of a star like Betelgeuse cannot be captured by imagining a smooth, enlarged sun. Its surface is restless on scales larger than entire planets. Convection lifts hot material upward through cells so large that a single cell can occupy a substantial fraction of the star's visible face. Gas cools, fuzz, rises again, and escapes. Pulsations alter the outer layers. Material blown away from the star accumulates around it, creating shells and irregular structures that record ongoing mass loss. The star is not merely large. It is in the process of becoming less contained. Its gravity still holds the main body together, but its outer regions are loose enough for matter to drift away and enrich the surrounding space. Elements formed inside massive stars, and elements created when some of them explode, later become part of new stars, planets, and living chemistry. The scale that diminishes the Sun is also part of the process that made rocky worlds possible. Betelgeuse is especially familiar because it is close enough in galactic terms to appear bright, and because its changes can be observed with unusual detail. Its famous dimming event drew attention to the instability of a supergiant atmosphere, but the event did not require an immediate stellar explosion. Observations supported a combination of surface cooling and dust formed from expelled material. The star's changing brightness revealed how easily a human eye can mistake appearance for size or final fate. A dimmer star is not necessarily becoming smaller. A brighter star is not necessarily becoming more stable. In evolved stars, light can change because of pulsation, dust, convection, temperature, or geometry. The visible point in Orion is therefore a complex object whose apparent simplicity comes from distance. Beyond Betelgeuse lie stars whose estimated dimensions are greater still. Scuti is often named among the largest known red supergiants by radius. It lies thousands of light-years away and is obscured by interstellar material, making its distance, temperature, and true size difficult to establish precisely. Earlier estimates placed it at extraordinary dimensions, while later analyses have revised some values and emphasized the uncertainties. This is not a minor technical problem. A star with an extended, pulsating atmosphere does not offer a neat edge, and any uncertainty in distance changes the inferred luminosity and radius. Scuti remains enormous, but its exact rank among the largest stars is not permanent. Other red supergiants and hypergiants can move above or below it as measurements improve. The category itself resists a simple leaderboard. The largest known star depends on whether size means radius, volume, mass, luminosity, or the reach of a surrounding atmosphere. Some stars may be wider but less massive than smaller blue stars. Some may be more luminous but physically more compact. Some are wrapped in thick shells of expelled gas that blur the distinction between the star and its environment. The comparison with the Sun is therefore most useful, not as a contest, but as a lesson in stellar diversity. Radius can grow enormously while average density falls. A red supergiant can be so extended that its outer layers are thinner than the best laboratory vacuums on Earth. Yet the star as a whole still contains several or many times the Sun's mass. It occupies a vast region without filling that region in the solid sense suggested by planetary intuition. Matter is concentrated toward the interior and becomes increasingly sparse toward the outside. If the Sun were somehow placed inside such an atmosphere, there would be no clear wall marking entry. The surrounding plasma would thicken gradually as the smaller star moved deeper. This diffuse structure helps explain how a star can reach a radius that would engulf the inner solar system without containing a proportional increase in mass. The largest stars are not simply dense objects expanded uniformly. They are gravitationally bound atmospheres stretched across distances normally associated with planetary orbits. Their lives are also brief. A star massive enough to become a red supergiant spends fuel rapidly, evolves quickly, and may end in a core collapse supernova, leaving behind a neutron star or black hole. The Sun will not follow that route. It lacks the mass required for such an explosion. It will expand, shed its outer layers more gently, and leave a white dwarf. In this sense, the Sun's modest size is tied to stability. Its slower fusion has given Earth billions of years under relatively steady light. A more massive star might have shone brighter, but its rapid evolution could have shortened the interval available for complex life. Cosmic grandeur does not imply habitability. The most enormous stars are among the least permanent. They appear late in their own histories and lose material as they approach their end. The Sun's ordinariness is therefore more subtle than insignificance. It is common in scale compared with giants, but valuable in duration and steadiness. From Earth, it remains the only star close enough to reveal a surface, an atmosphere, magnetic storms, and daily changes in detail. From the perspective of the galaxy, it is one moderate star among an enormous population. Betelgeuse, Uiscuti, and other supergiants show that stellar bodies can expand until the orbit of Earth becomes a small internal measure. Yet even these stars do not fill the spaces between neighboring systems. Their immense radii occupy only local islands within distances that remain far larger still. The Sun can be diminished by a giant star, and a giant star can still be separated from the next star by an emptiness so extensive that size alone no longer provides the most unsettling comparison. Between Earth and Mars, most of the journey contains no world at all. The planets look close in diagrams because a page cannot hold both their sizes and their distances honestly. A textbook may place Earth, Mars, Jupiter, and Saturn in a neat row, each body large enough to recognize and each orbit separated by a manageable gap. The arrangement is useful for naming the planets, but it quietly replaces the real solar system with a compressed one. In reality, the planets are tiny compared with the spaces they cross. Earth is nearly 13,000 kilometers wide, yet its average distance from the Sun is about 150 million kilometers. The planet's own diameter would have to be repeated more than 11,000 times to bridge that gap. Even the Moon, which appears close enough to share the same night sky, moves around Earth at an average distance of roughly 384,000 kilometers. All the other planets could be lined up side by side within that Earth-to-Moon distance under some definitions of their diameters, and there would still be room left over. The fact is often surprising because the Moon looks visually near, but apparent size is shaped by distance. The Moon is large enough and close enough to cover the Sun during a total eclipse, while the actual space separating it from Earth is wide enough to contain a chain of worlds. The first lesson of interplanetary scale is therefore not that the planets are large, it is that the emptiness around them is larger. A more faithful model makes the distortion obvious. If the Sun were represented by a sphere about 1 meter wide, Earth would be a bead less than 1 centimeter across, placed more than 100 meters away. The Moon would be a much smaller grain, only a little more than a quarter of a meter from that bead. Mars would orbit farther out, and Jupiter would be separated from the model Sun by well over half a kilometer. Neptune would lie several kilometers from the center. At that scale, the planets would be difficult to see without knowing exactly where to look, and almost the entire model would consist of open ground. A person walking through it would spend nearly all the time moving between objects, not examining them. This is the opposite of most visual representations, where the planets dominate and the gaps become background. In the true solar system, the gaps are the structure. Gravity acts across them. Light crosses them, and every planet spends its existence moving through them. The orbital arrangement also resists the expectation of even spacing. Mercury travels relatively close to the Sun. Venus lies farther out, and Earth follows at 1 astronomical unit. The average distance used as a basic measure inside the solar system, Mars circles at about 1.5 times that distance. Then, the pattern widens sharply. Jupiter lies more than 5 times Earth's distance from the Sun. Saturn is nearly twice as far out as Jupiter. Uranus is roughly twice as far from the Sun as Saturn. And Neptune orbits at about 30 times the Earth-Sun distance. The outer planets are not simply larger bodies placed a little beyond the inner worlds. They inhabit a much broader architecture. The region from the Sun to Mars occupies only a small central portion of the planetary system, while the journey from Jupiter to Neptune crosses billions of kilometers. A diagram that gives each orbit equal visual spacing turns this expansion into a false staircase. The real pattern is closer to a series of widening fields, with each outer world moving through a far larger ring of space than the one before it. Distance also changes with motion because the planets do not remain aligned. Earth and Mars may be relatively close on the same side of the Sun, or far apart with the Sun between them. A spacecraft cannot simply aim at the place where Mars appears and cross a fixed gap. It must enter an orbit around the Sun that intersects the future position of the planet. The journey becomes a problem of timing, velocity, and geometry. Even at the speeds achieved by modern spacecraft, travel to Mars takes months. Reaching Jupiter takes years, unless a mission follows a faster path with demanding energy requirements. Reaching Saturn, Uranus, or Neptune requires still more time, often with carefully planned gravitational encounters that use a planet's motion to alter the spacecraft's trajectory. These gravity assists do not remove the distance. They make passage through it possible by borrowing momentum from moving worlds. The long intervals between encounters reveal the real character of exploration. A mission may spend years in transit for a brief passage near its target. During that time, the spacecraft crosses no visible ocean of stars. The stars remain effectively fixed because they are vastly farther away, while the Sun slowly shrinks behind it and the destination grows only gradually ahead. The emptiness is not truly empty. Interplanetary space contains sunlight, magnetic fields, charged particles, dust, plasma, and occasional fragments of rock or ice. Comets release gas and dust. Asteroids occupy broad populations rather than forming a dense barrier. The solar wind streams outward from the Sun, carrying magnetic influence through the planetary system. Yet, the density of matter is extraordinarily low compared with anything on Earth. A spacecraft can travel for millions of kilometers without passing close to a substantial object. The asteroid belt between Mars and Jupiter is often pictured as a crowded field of tumbling rocks, but its members are spread through an enormous volume. The total mass of the belt is only a small fraction of the Moon's mass, and the distances between larger asteroids are generally vast. Missions pass through the region without weaving continuously around obstacles, The popular image of constant collision comes from compressing distance until separate bodies appear crowded. Once accurate spacing is restored, the belt becomes another example of how little matter is needed to occupy a great orbital zone. The same distortion affects the rings of planets. Saturn's rings look dense from afar because countless particles overlap along the line of sight, but each particle follows its own orbit inside a broad, thin disk. The solar system repeatedly produces structures that seem solid only because distance blends their components together. Close examination separates the visible form into motion and space. Light provides one of the clearest clocks for these distances. Sunlight reaches Earth in a little more than 8 minutes. It takes much longer to reach the outer planets, crossing the orbit of Jupiter after many tens of minutes and reaching Neptune after several hours. A radio signal travels at the speed of light. So, communication with spacecraft inherits the same delay. Near Mars, a message can require several minutes to travel one way, with the exact time changing as the planets move. Near Neptune, a one-way signal takes hours. Commands cannot be corrected instantly. A spacecraft must carry enough autonomy to protect itself, manage routine operations, and respond to unexpected conditions while Earth waits for information that is already old when it arrives. Distance becomes operational. It changes how machines are designed, how missions are controlled, and how much trust must be placed in systems acting beyond immediate human reach. The delay also reveals that there is no single shared present across the solar system in the ordinary conversational sense. Earth sees the sun as it was minutes earlier. A distant spacecraft reports conditions that occurred hours before the signal reaches mission control. Every observation arrives from the past because information needs time to cross space. On Earth, that delay is usually too small to notice. Between planets, it becomes part of the environment. Emptiness, therefore, shapes both perception and action. It makes worlds appear near in the sky while keeping them physically isolated. It allows gravity to organize broad systems without filling the intervening regions with matter. It forces exploration to depend on prediction rather than immediate response. It turns light into both messenger and limit. Most of all, it changes the meaning of a planetary neighborhood. The planets share one star, but they do not sit together like objects on a table. Each occupies a narrow moving zone inside an expanse where almost nothing solid is found. Earth is not beside Mars in any everyday sense. Jupiter is not just beyond the asteroid belt. Neptune is not merely the last marble in a row. These worlds are separated by intervals so wide that their sizes become secondary. The solar system is a set of small islands carried through a deep gravitational sea, and even that sea continues far beyond the orbit of the outermost major planet. The familiar planetary map ends at Neptune, but the Sun's domain does not. Beyond the last giant world, smaller bodies, frozen reservoirs, and the fading pressure of the solar wind extend the question of where the solar system truly ends into distances more difficult still. Beyond Neptune, the solar system does not end with a wall, a final orbit, or a clean line drawn through darkness. It thins. The large planets are left behind. Sunlight weakens, and the spaces between objects become wider. But the sun continues to shape motion far beyond the last familiar world. The first broad region outside Neptune is the Kuiper Belt, a population of icy bodies spread through a flattened zone around the sun. Pluto belongs to this region, though it is only one member among many. Some Kuiper Belt objects are small fragments, while others are large enough for gravity to pull them into rounded shapes. They preserve water ice, methane, nitrogen, and other frozen materials that formed in the cold outer reaches of the young solar system. Their surfaces are ancient but altered by impacts, radiation, and weak internal heat. The Kuiper Belt is not a bright ring packed tightly with objects. It is sparse. A spacecraft can cross it without seeing a continuous field of frozen worlds because the bodies are separated by enormous distances. That pattern begins near Neptune and extends outward for billions of kilometers. Yet it remains only the first extension beyond the planetary system. Its structure also carries evidence of migration. The giant planets did not necessarily form exactly where they orbit now. Their gravitational interactions in the early solar system scattered smaller bodies, shifted resonances, and rearranged whole regions. Neptune in particular shaped the Kuiper Belt, trapping some objects in repeating orbital relationships and sending others into more elongated paths. Pluto completes a set number of orbits, while Neptune completes another, allowing the two bodies to avoid close encounters despite crossing ranges in distance. This rhythm is the survival of a stable pattern after a chaotic beginning. Other objects follow detached or extreme orbits that carry them far beyond the main belt. Their paths raise questions about what shaped them. Some may have been scattered by the known planets. Some may record the gravitational influence of passing stars during the Sun's birth within a stellar cluster. A few have also encouraged speculation about an undiscovered distant planet, though no such world has yet been confirmed. The farther these bodies travel, the more the solar system becomes a record of forces that acted billions of years ago and have left only orbital geometry behind. Past the main Kuiper Belt lies the scattered disk, a more dispersed population whose members can move on steeply tilted and highly elongated paths. Some return toward Neptune before traveling far outward again. Their orbits make the outer solar system less like a set of rings and more like a layered volume, with objects moving above and below the plane, followed by most planets. The Sun still dominates their motion, but its hold is weaker at greater distance, and the influence of the wider galaxy begins to matter more. A passing star does not need to approach closely enough to threaten the planets in order to disturb small bodies at the edge of the Sun's domain. The collective gravity of the Milky Way can also alter remote orbits over immense spans of time. At such distances, the solar system is no longer isolated from its galactic setting. Its outermost members respond both to the Sun and to the environment through which the Sun itself travels. Another boundary is defined not by orbiting bodies, but by the solar wind. Charged particles stream outward from the Sun, carrying embedded magnetic fields and creating an enormous bubble in the surrounding interstellar medium. This bubble is the heliosphere, Earth, the other planets, the Kuiper Belt, and much of the known outer system lie within it. Near the Sun, the solar wind moves rapidly. As it travels outward, it expands and becomes thinner until it begins to encounter gas and magnetic fields between the stars. The first major transition is the termination shock, where the solar wind slows abruptly from supersonic speed. Farther out lies the heliosheath, a turbulent region where solar material continues to decelerate and mix in complex ways. Beyond that lies the heliopause, the boundary where the outward pressure of the solar wind is balanced by the surrounding interstellar environment. The heliopause is often described as the edge of the solar system, but this is only one definition. It marks the limit of the Sun's particle-dominated bubble, not the end of its gravity. Spacecraft have crossed this threshold. Voyager 1 entered interstellar space by passing beyond the heliopause, followed later by Voyager 2 at a different distance and under different local conditions. Their crossing showed that the boundary is not a perfect sphere. The heliosphere is shaped by the solar cycle, by the direction of the Sun's movement through the local interstellar medium, and by external magnetic fields. It may resemble a broad, changing cavity with an asymmetric form rather than a simple bubble with a fixed radius. Even after crossing the heliopause, the Voyager spacecraft remain gravitationally connected to the Sun. They have left the heliosphere, but they have not escaped the solar system in the orbital sense. That distinction reveals why the system has no single natural edge. A particle boundary, an orbital boundary, and a practical boundary for exploration can all lie at different distances. The Sun's light becomes weak long before its gravity ceases to matter, and its gravity may influence objects far beyond the region reached by its solar wind. The most distant proposed reservoir is the Oort Cloud, Avast, roughly spherical collection of icy bodies thought to surround the solar system. Unlike the Kuiper Belt, it has never been directly imaged as a complete structure. Its existence is inferred mainly from the paths of long-period comets, which arrive from many directions and follow orbits, suggesting an origin far beyond the planets. These comets may spend millions of years moving slowly through the outer darkness before a gravitational disturbance sends them inward. As they approach the Sun, heat releases gas and dust from their frozen surfaces, producing bright comas and tails. They become visible briefly, but spend most of their existence where sunlight is faint and orbital motion is slow. The Oort cloud may begin thousands of times farther from the Sun than Earth and extend outward to distances measured in fractions of a light year or perhaps more. Its exact dimensions, population, and total mass remain uncertain because its members are too small, cold, and distant to observe easily. The cloud may contain an inner region with a somewhat flattened or torus-like form, and an outer region distributed more nearly in all directions. Its bodies were probably formed much closer to the Sun, among the giant planets, before gravitational encounters scattered them outward. Most scattered objects may have escaped completely, but some were slowed or redirected by the gravity of nearby stars and the galactic environment until they settled into remote, weakly bound orbits. In this way, the Oort cloud may be both part of the solar system and a product of the Sun's early surroundings. Its outer edge approaches a threshold where the Sun's gravity competes with passing stars and the Milky Way itself. Objects there are only loosely attached. A modest disturbance accumulated over enough time can change their paths, send them inward, or remove them from the solar system entirely. The boundary, therefore, behaves less like a border and more like a region of declining allegiance. Close to the Sun, an object's orbit is clearly solar. Far away, the same object moves within a field of competing influences. There may be no precise point at which ownership changes. The Oort cloud also changes the meaning of interstellar distance. Proxima Centauri is more than 4 light-years away, but the outermost reach of the Sun's comet reservoir may extend a significant fraction of the way toward neighboring stars. If other stars possess similar clouds, the space between systems may contain overlapping histories of scattered ice. Even if the stable gravitational domains remain distinct, the solar system would then be far larger than the planetary diagrams suggest, but also far more diffuse. Its broadest structure would contain almost no mass per unit of volume. A boundary measured in light months or fractions of a light year could be made from bodies so widely separated that each moves in near isolation. This is the final reversal at the solar system's edge. Greater size does not produce greater fullness. The system grows outward by becoming emptier. Neptune marks the last major planet. The Kuiper Belt preserves a flattened population of icy remnants. The scattered disk extends those paths into more extreme orbits. The heliopause marks the weakening frontier of the solar wind, and the Oort cloud may carry the Sun's gravitational influence almost into interstellar space. None of these boundaries fully replaces the others. Each answers a different question about where the sun stops dominating matter. Together, they show that a star system is not a compact arrangement of worlds, but a hierarchy of influences fading across immense distance. Yet even the most generous boundary remains local. Once the sun's hold finally gives way, the nearest neighboring star is still separated by a gulf that light itself requires years to cross. Proxima Centauri is the nearest known star to the sun, yet its light still requires more than 4 years to reach Earth. That single fact changes the meaning of nearness. Inside the solar system, distance is measured in minutes or hours of light travel time. Between stars, the same measure expands into years. Proxima Centauri lies about 4.25 light-years away, which means every observation of it arrives from a past already several years old. The star seen in a telescope is not the star as it exists at that instant, but the star as it was when its light began crossing the gulf between systems. Even this nearest neighbor remains beyond direct contact, separated not by a wider version of interplanetary space, but by a scale that makes the solar system itself look compact. A light-year is the distance light travels through vacuum in 1 year, nearly 10 trillion kilometers. It is not a measure of time, though time is built into it. To cross 1 light-year, a beam of light moves for an entire year without slowing, passing far beyond the orbit of Neptune, beyond the heliopause, and through a region where the sun's visible influence has faded almost completely. Proxima Centauri is more than 4 such distances away. No human vehicle has approached anything close to that speed. The Voyager spacecraft travel fast enough to escape the planets and continue into interstellar space, but at their present velocities, they would need tens of thousands of years to cover a distance comparable to the gap between the Sun and Proxima Centauri. They are not aimed there, and their instruments will cease operating long before such a crossing could be completed. But the comparison reveals the true isolation of neighboring systems. Interstellar travel is not merely a longer mission. Under present technology, it belongs to a different category of duration. Proxima Centauri itself is a red dwarf, a small, cool star, far less luminous than the Sun. It is part of the Alpha Centauri system, which also includes the brighter stars Alpha Centauri A and Alpha Centauri B. Those 2 stars orbit one another, while Proxima remains associated with them across an immense separation. From Earth, the system appears as one of the closest stellar landmarks. But closeness does not make it easy to understand. Proxima is too faint to see with the unaided eye, despite being the nearest star beyond the Sun. The most familiar stars in the night sky are often not the nearest. They appear prominent because they are intrinsically bright, because they are massive, or because they occupy a favorable combination of distance and luminosity. Proxima offers the opposite lesson. The nearest star can remain invisible, while much more distant stars dominate the sky. Perception again depends on what light reveals, not on physical proximity alone. At least 2 planets have been reported around Proxima Centauri, including one world known as Proxima Centauri b. It orbits much closer to its star than Earth orbits the Sun. Yet because Proxima is faint and cool, that orbit lies within the region where temperatures might permit liquid water under suitable atmospheric conditions. The phrase habitable zone describes only an energy range. It does not confirm oceans, air, life, or even a stable surface environment. Red dwarfs can produce strong flares and energetic radiation, and Proxima is magnetically active. A planet close enough to receive moderate warmth may also be exposed to repeated bursts capable of eroding or altering an atmosphere. Its presence is scientifically important, but it does not soften the distance. A potentially temperate planet around the nearest star is still more than 4 light-years away. Even a radio message sent toward it would require more than 4 years to arrive, and any reply would require the same interval to return. A single exchange would unfold across nearly a decade. Communication at interstellar scale is therefore not conversation. It is correspondence between distant epochs. The gap becomes clearer through a physical model. If the sun were reduced to the size of a small fruit, Earth would be a grain circling several meters away, while Proxima Centauri would lie many hundreds of kilometers from the model sun, depending on the exact scale chosen. The entire planetary system, including its broad outer regions, would occupy only a tiny zone around one point, followed by an almost uninterrupted span before the next star appeared. The emptiness between the two would not be perfectly vacant. It would contain thin gas, dust, gran, magnetic fields, energetic particles, and perhaps small wandering bodies. But compared with any environment on Earth, or even with the already sparse space between planets, interstellar matter is extraordinarily diffuse. The stars are therefore not packed like lights on a ceiling. They are isolated islands separated by distances so great that their disks vanish into points even when viewed through powerful instruments. This spacing shapes the structure of the galaxy. Gravity binds stars to the Milky Way, but most stars do not interact closely with one another. They orbit the galactic center through a broad distribution, occasionally passing nearer to neighbors over millions of years. Yet, direct collisions between ordinary stars are extremely rare. Their physical sizes are too small compared with the gaps between them. Even when galaxies merge, their stars largely pass through the opposing system without striking other stars. The larger danger comes from changing gravitational fields, disrupted gas, and altered orbits, not from stellar surfaces meeting directly. A galaxy may contain hundreds of billions of stars and still be mostly empty. Great numbers do not imply crowding when the available volume is larger still. The Sun and Proxima Centauri are also moving. Their current separation is not permanent, and neither star occupies a fixed point in space. Both travel around the center of the Milky Way while carrying their planets and smaller bodies with them. Over tens of thousands of years, other stars will pass closer to the Sun than Proxima does now, and Proxima itself will eventually move farther away. The identity of the nearest star changes across deep time. Stellar neighborhoods are temporary arrangements formed by orbital motion through the galaxy. A star can remain the nearest neighbor longer than recorded civilization. The sky appears stable because human lives sample only a tiny portion of galactic motion. This motion also means that any interstellar journey must target a moving destination. A spacecraft aimed toward a nearby star would need to account for where the star will be after decades, centuries, or longer. It would need energy to accelerate, protection from radiation and dust, reliable navigation, and some way to slow upon arrival. At a significant fraction of light speed, even a grain of dust could strike with destructive energy. At lower speeds, the crossing becomes so long that machinery, power sources, and stored knowledge would need to endure across generations. Concepts such as laser-driven sails or fusion propulsion have been proposed, but no existing mission can send a substantial craft to another star within a human lifetime. The physics does not forbid all interstellar travel, but it imposes a severe cost in energy, engineering, and time. The nearest star, therefore, represents a threshold rather than a destination. It is close enough to measure in detail, close enough for its planets to become objects of study, and close enough to appear reachable in speculation. Yet its distance exposes how confined human activity remains. Every spacecraft ever launched, every radio signal sent intentionally or unintentionally into space, and every observation made from Earth begins within one small stellar system. Signals have traveled outward for decades, forming an expanding shell around the Sun. But that shell has reached only a tiny portion of the galaxy. Most of the Milky Way has not had time to receive any sign that technological life arose on Earth. Proxima Centauri lies just across the first narrow interval of that expansion. And even there, any detectable trace belongs to years already gone. The unsettling part is not that the nearest star is remote. It is that this remoteness is ordinary. The distance to Proxima Centauri is among the smallest gaps the galaxy offers. Beyond it, other stars lie 6, 10, 20, or hundreds of light years away, and the Milky Way continues for tens of thousands more. The first interstellar crossing does not bring the scale under control. It only reveals the unit from which larger stellar distances are built. The solar system, extended through the possible Oort Cloud and wrapped in the fading heliosphere, becomes one small gravitational island. Proxima Centauri marks the next island, not the shore of a larger continent. Between them lies enough darkness to outlast civilizations, machines, and perhaps entire species. And once that distance is understood, the Sun's location within the Milky Way can no longer be imagined as a point surrounded by nearby stars. It is a nearly invisible position inside a spiral system whose true dimensions make the nearest stellar gulf look local. The solar system does not occupy a central place in the Milky Way. It travels through a minor spiral feature called the Orion Arm, or Orion Spur, positioned between the larger Sagittarius and Perseus arms. This location is neither at the galactic center nor near the outermost edge. It is a local corridor of stars, gas, dust, and stellar remnants embedded within a much larger rotating disk. From Earth, the Milky Way appears as a pale band across a dark sky because the solar system looks through that disk from the inside. The glow is not a distant cloud suspended beyond the planets. It is the combined light of countless stars spread through the same galaxy that contains the Sun. Dust obscures much of the view, breaking the band into dark lanes and hiding large regions toward the center. What appears from the ground as a narrow strip is therefore an interior perspective through a structure far too broad to see as a whole. The Sun is one star among hundreds of billions, moving with its planets through a neighborhood that has no visible boundary and no sign marking its place. The Orion Arm itself is small compared with the major spiral arms. It contains prominent star-forming regions, bright nebulae, young clusters, and many ordinary stars. But it is not one of the galaxy's dominant structural features. The solar system lies within a local cavity of relatively thin interstellar gas known as the local bubble, probably shaped by ancient supernova explosions. This cavity stretches for hundreds of light years and contains hot, sparse plasma surrounded by denser clouds. Even the immediate stellar neighborhood is therefore part of a larger history. The space around the Sun has been altered by stars that lived, exploded, and disappeared long before the present arrangement of nearby systems. The solar system moves through this changing medium while the Sun's magnetic bubble pushes against it, creating the heliosphere described by the Voyager crossings. What seems like empty space near the planets is already connected to the galactic environment. The Milky Way does not begin beyond the nearest stars. It is present in the gas between them, in the gravity guiding their motion, and in the chemical elements from which the Sun and planets formed. To locate the solar system within the galaxy, distance must be measured from a center that cannot be seen directly in visible light. The galactic center lies toward the constellation Sagittarius, hidden behind thick clouds of dust. Radio, infrared, and other observations reveal a dense region crowded with stars and shaped by a supermassive black hole called Sagittarius A star. The solar system lies roughly 26,000 light-years from that center, about halfway to two-thirds of the way outward, depending on how the galaxy's edge is defined. This is far enough to avoid the most crowded central regions, yet close enough to remain well inside the stellar disk. From above the galaxy, if such a view were possible, the sun would be almost impossible to identify. The spiral pattern would dominate. The central bulge would appear bright, and the solar system would occupy a point too small to resolve without a deliberate marker. The entire planetary system, including the distant Oort Cloud, would be smaller than a faint grain within one segment of one arm. The sun is not fixed at that point. It orbits the galactic center along with nearby stars, carrying Earth through a path so large that one revolution takes roughly 230 million years. This interval is sometimes called a galactic year. Since the formation of the solar system, the sun may have completed only about 20 such orbits. The entire history of complex life on Earth occupies only a portion of one galactic circuit, while recorded human history covers almost none of it. Continents move, species rise and vanish, oceans open and close, and the sun advances only slightly along its orbit. The familiar constellations change because neighboring stars have their own motions, but the larger galactic revolution remains far too slow for direct human experience. The night sky gives the impression of a fixed celestial arrangement because each life samples only a narrow instant of that motion. On longer timescales, the sun passes through changing stellar neighborhoods, crosses regions of different gas density, and moves above and below the galaxy's midplane in a slow oscillation. Its path is not a simple circle drawn on a flat surface. The galaxy contains a bar, spiral structure, clouds, star clusters, and gravitational irregularities that complicate every orbit. The sun follows the combined gravitational field of the Milky Way, responding to the distribution of visible matter and to the much larger unseen mass attributed to dark matter. Even its long-term route is part of a system whose full structure must be inferred rather than directly observed from outside. The speed of this motion is immense by terrestrial standards. The sun travels around the galaxy at hundreds of thousands of kilometers per hour. Yet the Milky Way is so large that this velocity produces no visible rush. Earth moves with the sun, the planets, the Kuiper Belt, and the distant comet reservoir, all carried together through interstellar space. Nothing on the ground feels this movement because every local object shares it. The same principle makes orbital motion around the sun imperceptible in daily life. Motion becomes noticeable through changes relative to nearby surroundings, and the galactic environment is too distant for its shift to appear quickly. The solar system can cross millions of kilometers, while the nearest stars seem almost unchanged. Scale turns extraordinary speed into apparent stillness. This orbit also removes the comforting idea that the solar system forms a stable island independent of the galaxy. Its structure survives because the sun's gravity dominates locally, but the whole system belongs to a larger gravitational hierarchy. The moon circles Earth. Earth circles the sun. The sun circles the center of the Milky Way. The galaxy itself moves within a group of galaxies. At each level, what seemed like a foundation becomes an orbiting component. The change is not merely rhetorical. The solar system's direction, velocity, and long-term environment are set by a structure vastly larger than itself. Even the plane of the planetary orbits has no special alignment with the plane of the Milky Way. The two systems formed through different histories and occupy different orientations, The planets, therefore, do not sweep around the galaxy like objects arranged neatly on a horizontal disk within a larger horizontal disk. The entire planetary system is tilted relative to the galactic plane and carried through it as a compact, moving unit. Attempts to draw the solar system's path as a dramatic helix can be misleading because all motion depends on the chosen frame. But the underlying point remains useful. The planets continue orbiting the Sun, while the Sun itself travels around the galaxy. There is no final stationary background inside this hierarchy. The local stellar neighborhood adds another layer of smallness. Within a few dozen light-years are red dwarfs, Sun-like stars, white dwarfs, binary systems, and planetary systems in many stages of discovery. These objects form no permanent family. Some are approaching, some receding, and all follow separate galactic orbits over tens of thousands of years. The list of nearest stars changes. Over millions of years, stellar encounters can disturb the remote edges of comet clouds without threatening the inner planets directly. The solar system's present surroundings are temporary, just as the arrangement of continents on Earth is temporary. Stability exists, but only within a limited interval and scale. The Sun may have formed in a cluster with many sibling stars that later disperse through the galaxy. Those siblings, if they can be identified at all, are now mixed among countless unrelated systems. The birthplace of the solar system is no longer a visible home. Galactic motion has erased the original neighborhood while preserving only chemical and orbital clues. From Earth, the Milky Way can still feel intimate because it is visible without instruments under dark skies. Its band has guided calendars, navigation, and stories for thousands of years. Yet that familiarity conceals the scale of the structure being seen. The pale light crosses distances ranging from nearby stars to remote regions of the disk. Some of it began its journey before human civilization existed. The band is a layered view through space and time, with stars at different distances merged into one luminous field. Within that field, the Sun contributes almost nothing to the galaxy's appearance as a whole. Remove it, and the Milky Way would remain visually unchanged from nearly every distant vantage point. Remove the solar system, and no spiral arm would lose its shape. No major gravitational pattern would shift. The local absence would matter absolutely to Earth, but scarcely at galactic scale. This is the sharper meaning of being a speck in the Milky Way. The solar system is not only small in size, it is dynamically minor. One ordinary system following a path set by the combined mass of the galaxy. Its planets, histories, and living world occupy a point that cannot be distinguished from the surrounding stellar population without precise knowledge. Yet the Orion Arm, the galactic orbit, and the hidden center provide only a location. The larger reduction comes from understanding the full dimensions of the system that contains them, because the Milky Way is not merely a band across the sky. It is a galaxy so wide that light needs around 100,000 years to cross it. The Milky Way is wide enough that light, moving faster than anything with mass can travel, requires about 100,000 years to cross its stellar disk from one side to the other. That figure is already an approximation, because a galaxy has no sharp outer wall. The bright disk fades gradually into a more diffuse population of stars, gas, and dark matter, and different methods produce different boundaries. Even so, the order of scale is secure. A beam of light, leaving one edge when early human ancestors were beginning to spread across new landscapes on Earth, might only now be reaching the opposite side. A radio signal sent from the solar system today would need tens of thousands of years to reach many regions of the galaxy, and tens of thousands more for any reply to return. The Milky Way is therefore not a place that can be surveyed through travel on human timescales. It is reconstructed from light, motion, chemistry, and geometry, with Earth fixed inside the structure it is trying to measure. That interior position makes the task unusually difficult. From outside, the galaxy might appear as a barred spiral, with a bright central region, curved arms, dark dust lanes, and a thin luminous disk surrounded by a faint halo. From Earth, those features overlap along the line of sight. Nearby stars mix with distant ones. Dust hides the center. Gas clouds absorb visible light. The shape of the whole must be inferred from partial views, as though a city were mapped from one neighborhood while fog concealed many streets and no observer could rise above the rooftops. Radio astronomy penetrates much of the dust by tracing hydrogen and molecules in the interstellar medium. Infrared observations reveal stars hidden behind obscuring clouds. Stellar distances are estimated through parallax, brightness, pulsation, and other methods, while the motions of stars and gas expose the gravity organizing the disk. Each technique fills a different part of the map, yet the Milky Way remains a structure known from within, rather than photographed as a complete object. Its disk is not a flat sheet. The thin, stellar disk, where the Sun and many younger stars reside, has a thickness of roughly 1,000 light-years in the local region, while an older thick disk extends farther above and below the central plane. Gas and dust gather mostly near that plane, forming clouds that can collapse into new stars. The spiral arms are not rigid bands of the same stars permanently locked together. They are broad patterns of enhanced density and star formation through which stars and gas can move. Bright young stars make the arms visible because they do not live long enough to drift far from their birthplaces. But much of the galaxy's mass lies in older, dimmer stars spread throughout the disk. Near the center, the galaxy becomes more crowded. A bar of stars crosses the inner region, feeding into spiral structure and guiding gas through complex orbits. Around the nucleus lies a dense bulge containing older stars, compact remnants, dust, and energetic processes hidden from ordinary sight. At the very center sits Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. This black hole is enormous compared with any planetary object, yet it contributes only a tiny fraction of the galaxy's total mass. The Milky Way is not held together mainly by its central black hole. Stars far from the center orbit because of the combined gravity of the galaxy's stars, gas, remnants, and dark matter. The black hole dominates only the innermost region. Farther out, it becomes one compact component inside a much larger gravitational system. The Milky Way contains stars of almost every major kind. Small red dwarfs are probably the most numerous, though their faintness makes them difficult to count across great distances. Stars like the Sun form only part of the population. Massive blue stars burn brightly for short lives. Red giants expand after exhausting hydrogen in their cores. White dwarfs remain as dense stellar remnants. Neutron stars and black holes preserve the collapsed cores of massive stars. Binary and multiple systems are common, and planets appear to form around many different kinds of stars. Estimates of the total stellar population vary, but the galaxy likely contains hundreds of billions of stars. That uncertainty is itself revealing. The Milky Way is so large, and so much of it is obscured or faint, that even the number of its stars cannot be counted directly. Astronomers estimate the total by sampling regions, measuring the galaxy's light and mass, and modeling populations too dim to observe individually. The Sun is one member of a population whose exact size exceeds direct enumeration. If every star were represented by a grain of sand, The collection would form an immense mass, but even that image would compress the spacing beyond recognition. Most grains in such a model would need to be separated by large distances relative to their own size. The galaxy's vastness comes from both number and emptiness. It contains an extraordinary population of luminous objects. Yet the average separation between stars remains measured in light years. The disk can be crowded by galactic standards while still leaving nearly all of its volume empty by terrestrial standards. Molecular clouds are denser than the surrounding interstellar medium, but they are still far thinner than any vacuum created in an ordinary laboratory. Their importance comes from scale. A cloud spread across dozens of light years can contain enough gas and dust to produce thousands of stars, even when its particles are widely separated. Gravity works slowly across that diffuse material, drawing denser regions inward until collapse, heating, and fusion begin. The Milky Way is therefore active not because it is full in the everyday sense, but because small densities integrated across enormous volumes become substantial. Its total visible matter is immense, but observations of orbital motion indicate that visible matter is not enough to explain how the galaxy rotates. Stars far from the center move faster than expected. If gravity came only from the stars and gas that telescopes can detect, the leading explanation is a broad halo of dark matter surrounding the luminous galaxy. Dark matter does not emit, absorb, or reflect light in the ordinary way, but its gravity appears to shape the motions of stars, the stability of the disk, and the growth of galaxies over cosmic time. The Milky Way's true scale is therefore larger than the bright spiral seen in illustrations. The stellar disk sits inside a much wider, roughly spherical dark matter halo that may extend for hundreds of thousands of light years. A faint stellar halo also surrounds the disk, containing old stars and globular clusters on wide, tilted orbits. Streams of stars arc through this halo. Remnants of smaller galaxies and star clusters stretched apart by the Milky Way's gravity. These structures revealed that the galaxy grew partly by absorbing other systems. The Milky Way is not a finished object formed in isolation. It is the current stage of a long history of mergers, accretion, star formation, and internal change. Dwarf galaxies continue to orbit it, and some are being disrupted as their stars are pulled into elongated streams. The disk itself can warp, spiral patterns can shift. The central bar can influence the flow of gas. Stars are born, age, scatter heavier elements, and leave remnants. On human timescales, the galaxy appears permanent, but over billions of years, it is a changing ecosystem of matter and gravity. The solar system participates in that history without controlling any part of it. Its orbit carries it through changing regions while nearby supernovae, stellar encounters, and interstellar clouds leave subtle records in planetary material, yet the entire system remains too small to alter the galaxy's form. Even the Sun's long life is brief compared with some red dwarfs, and its gravitational reach is negligible beside the structure that guides its orbit. To cross the Milky Way at the speed of the fastest current spacecraft would require a span far longer than the age of human civilization and likely longer than the time modern humans have existed. At the speed of light, the crossing still consumes about 100,000 years. That limit removes any ordinary sense of simultaneity from the galaxy. Light reaching Earth from the far side began its journey when Earth's own surface, climate, and living populations were different. Observing the Milky Way means seeing many eras at once. Nearby stars appear as they were years ago. Distant regions appear as they were tens of thousands of years ago. The galaxy is not presented in a single present image, because no signal can carry the state of the whole to one observer instantly. Its true scale includes this spread in time. The Milky Way is a structure so broad that its own light cannot report all of it at once. Yet even this immense system, with hundreds of billions of stars, a central black hole, spiral arms, stellar halos, satellite galaxies, and an unseen dark matter envelope, is only one galaxy. Its scale overwhelms the solar system. But the universe contains other galaxies equal to it, larger than it, and gathered into structures that will reduce it in turn. Andromeda is the first galaxy large enough and close enough to make the Milky Way lose its apparent uniqueness. Seen from Earth, it is only a faint patch under dark skies. But that dim glow belongs to a spiral system containing hundreds of billions of stars and stretching across a distance comparable to, and perhaps somewhat greater than, the Milky Way. Its light takes more than 2 million years to reach Earth. So the galaxy appears, not as it is now, but as it existed long before modern humans. The apparent softness of the object is therefore another effect of distance. A structure with spiral arms, star-forming regions, dust lanes, globular clusters, stellar remnants, and a central black hole is compressed into a haze barely wider than a thumb held at arm's length. The Milky Way and Andromeda form the two dominant members of the local group, a gravitational association that also contains the Triangulum Galaxy and dozens of smaller galaxies. Within that small collection, the Milky Way may seem important, but even there it is not alone at the top. Andromeda may contain more stars, while the Milky Way may have a comparable or even greater total mass once dark matter is included. The exact ranking depends on how each galaxy is measured, and those measurements continue to improve. The important fact is not which galaxy wins a narrow comparison. It is that two large spiral galaxies occupy the same local neighborhood, accompanied by many smaller systems, and neither is exceptional enough to define the class. Their broad similarities reveal that the Milky Way is one expression of a common galactic form rather than a singular cosmic structure. Both contain disks, central bulge, halos of old stars, satellite galaxies, dark matter, and ongoing histories of interaction. Both have grown through mergers and the gradual capture of smaller systems. Both continue to form stars from cold gas, though at different rates and in different regions. Both carry evidence of earlier collisions in stellar streams and disturbed outer structures. The galaxy that contains the Sun is therefore not a completed island set apart from the rest. It belongs to a population shaped by the same large-scale processes that build galaxies throughout the universe. The comparison becomes more direct because the Milky Way and Andromeda are moving toward one another. Their mutual gravity has been drawing them together, and in several billion years, their disks are expected to pass through and merge. The event sounds violent only when imagined at the scale of planets or stars. At galactic scale, direct stellar collisions remain unlikely because the stars are so small compared with the distances between them. The more important changes occur through gravity. Orbits are altered. Gas clouds are compressed. Star formation may intensify in some regions, and both disks can be stretched into tidal tails before settling into a different structure. The central black holes may eventually form a pair and merge after losing orbital energy through interactions with surrounding stars and gas. What emerges may resemble a large elliptical galaxy or another disturbed form rather than a clean spiral. The solar system, if it still exists in recognizable form by then, could be moved to a new galactic orbit without passing close to another star. The merger would radically transform the appearance of the night sky. Yet, it would not make either galaxy unusual. Mergers are a normal part of galactic evolution. Larger galaxies often grow by absorbing smaller ones, And many of the most massive systems are products of repeated collisions beyond the local group. The limits of the Milky Way become clearer. Some spiral galaxies extend much farther across their disks, with longer arms, larger stellar populations, and more massive dark matter halos. Others are smaller, fainter, and less organized. Barred spirals, unbarred spirals, flocculent galaxies with fragmented arms, and grand design spirals with prominent sweeping patterns all occupy the same broad family. The Milky Way is a barred spiral, but even that classification places it among many. Its particular arrangement of arms and central structure matters locally, yet it does not set a universal standard. Galaxies can differ in gas content, star formation, age, metallicity, environment, and central activity, while still sharing a similar outward form. A galaxy seen face-on may display bright blue star forming regions along its arms. Seen edge-on, the same type can appear as a thin disk divided by dust. Perspective changes appearance, while physical history determines the deeper structure, and spiral galaxies are only one major category. Elliptical galaxies can contain enormous populations of stars arranged in broad, smooth shapes without the thin disks and distinct arms that define spirals. Many contain mostly older stars and relatively little cold gas. So, new star formation proceeds slowly. Some are modest in size. Others are giants that dominate the centers of galaxy clusters. A central giant elliptical can extend for hundreds of thousands of light-years through its outer stellar envelope, with a mass far beyond that of the Milky Way. These systems often sit where gravitational interactions have been strongest. Having grown through repeated mergers and the capture of surrounding galaxies, their stars move on a wide range of orbits rather than sharing the ordered rotation of a thin disk. The result is not a larger spiral, but a different gravitational architecture, one built from accumulated stellar populations. In the centers of some giant ellipticals lie black holes containing billions or even tens of billions of times the mass of the Sun. Such black holes still represent only part of the total galaxy, but they reveal how far galactic growth can proceed beyond the local scale. The Milky Way's central black hole contains about 4 million solar masses, immense beside any star and yet modest beside the central objects in the greatest galaxies. Even Sagittarius A star is reduced when the comparison moves outward. Some galaxies are also surrounded by diffuse envelopes of stars, extending far beyond the bright region usually shown in photographs. The visible edge can therefore underestimate the full system, just as the bright disk of the Milky Way underestimates its dark matter halo. A giant galaxy may influence space across distances approaching the separation between smaller galaxies. Its satellites orbit inside a broad gravitational domain, and stars torn from disrupted companions can form streams or shells around it. The galaxy becomes less a single luminous object than the center of a layered system. Yet size does not always mean brightness. Ultra-diffuse galaxies can spread a modest number of stars across a large area, making them faint despite their width. Compact galaxies can contain dense stellar populations within small volumes. Some galaxies are rich in gas but poor in stars. Others have exhausted or expelled much of the gas needed for new star formation. The universe does not arrange galaxies along one simple ladder from small to large. Radius, mass, luminosity, star count, density, and dark matter content can vary independently. The Milky Way occupies only one combination among many. Its familiar spiral arms and moderate central black hole are neither minimum nor maximum, neither standard nor exception. Quasars and other active galactic nuclei widen the difference further. When gas falls toward a supermassive black hole, it can form a hot accretion disk and release extraordinary amounts of radiation before crossing the event horizon. A galaxy with an active nucleus may outshine the combined light of its stars, even though the luminous region around the black hole is small compared with the galaxy itself. The Milky Way's center is comparatively quiet at present. Sagittarius A star consumes little material and produces only modest activity. Other galaxies show what the same basic structure can become under different conditions. Jets can extend far beyond the host galaxy, carrying energy into surrounding gas and influencing future star formation. The galaxy is no longer merely a collection of stars. It becomes an engine linking a compact central region to an environment hundreds of thousands or even millions of light-years across. This variety removes the last temptation to treat the Milky Way as the natural scale of a galaxy. It is large enough to contain hundreds of billions of stars and small enough to be surpassed by systems assembled through longer or more violent histories. It is active enough to form new stars and quiet enough to lack the brilliant nucleus seen in quasars. It has absorbed smaller galaxies and will itself merge with Andromeda. It contains a massive dark halo, yet belongs to a local group whose total structure is governed by the combined mass of several members. From Earth, the Milky Way feels total because every visible star that can be resolved without powerful instruments belongs to it. Beyond that apparent ceiling lies a universe filled with galaxies whose forms, mass, and histories make the home galaxy one example rather than the final frame. The reduction is complete only when those galaxies are no longer considered separately, because they too gather under gravity into groups, clusters, filaments, and walls that turn even the largest individual galaxy into one bright knot within a much greater cosmic structure. The local group is already larger than any single galaxy. Yet, it is only a modest gathering inside a much wider pattern. The Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies remain bound together by their combined gravity across a region several million light-years wide. Most of the visible members are dwarfs, faint systems with far fewer stars than the two dominant spirals. Some orbit the Milky Way. Others gather around Andromeda. A few occupy more isolated paths through the group. Their motions are slow by human standards, but decisive over billions of years, allowing galaxies to merge, satellites to be stripped, and streams of stars to form where smaller systems are pulled apart. The local group is therefore not a static collection. It is a small gravitational ecosystem in which the largest members reshape the smallest and the whole structure gradually evolves toward deeper consolidation. Even so, it contains too little mass and too few galaxies to rank among the great clusters of the universe. Its importance comes from familiarity, not scale. It is the immediate galactic neighborhood, the first level at which the Milky Way becomes one component of something larger. Beyond it lies a broader arrangement of nearby groups and clusters that has often been described through the language of superclusters. The local group belongs to a region associated with the Virgo cluster, a much richer concentration of galaxies tens of millions of light-years away. The Virgo cluster contains well over 1,000 known galaxies, including giant ellipticals, spirals, lenticular systems, and many dwarfs. Its gravity shapes the motions of surrounding groups, though the local group is not simply falling into it along a straight line. The nearby universe contains many overlapping influences, with matter distributed unevenly across filaments, sheets, clusters, and voids. Motion reflects the combined pull of this larger landscape. The local group and Virgo cluster can be placed within a wider structure known as Laniakea. a vast basin of galactic motion extending across hundreds of millions of light-years. The name describes a region in which galaxies tend to move along gravitational pathways toward a broad area called the Great Attractor. This does not mean that one hidden object sits at a central point and pulls everything inward like a star controlling planets. The Great Attractor is better understood as part of a large concentration of mass, including galaxy clusters and dark matter, embedded within an even broader network. Galaxies respond to the full distribution around them. Their paths reveal where matter lies, even when much of that matter is not directly visible. At this scale, location is defined less by a clean boundary than by patterns of flow. A supercluster is not always a tightly bound object that will remain intact forever. Cosmic expansion can separate large regions faster than gravity can gather them together, leaving only the densest cores permanently connected. The word cluster suggests a compact assembly, but a supercluster may be a temporary contour drawn across a moving gravitational field. Rich galaxy clusters are more tightly organized. They can contain hundreds or thousands of galaxies bound inside a common halo of dark matter and immersed in extremely hot, thin gas. That gas fills the space between galaxies and can contain more ordinary matter than all the cluster's stars combined. It glows mainly in X-rays because collisions and compression have heated it to temperatures of millions of degrees. A galaxy cluster is therefore not merely a crowd of galaxies. It is a deep gravitational well holding stars, dark matter, superheated plasma, magnetic fields, and the remnants of countless interactions. Galaxies moving through the cluster can lose gas as pressure from the surrounding plasma strips material away. Without cold gas, star formation slows. Encounters can distort disks, trigger bursts of star formation, or transform spirals into smoother systems. The cluster environment changes its members. Just as giant planets shape moons and the Milky Way shapes dwarf galaxies, but on a much greater scale. At the centers of many clusters sit enormous elliptical galaxies built through repeated mergers. Their diffuse outer stars blend into the cluster itself, making it difficult to decide where one galaxy ends and the larger structure begins. Even these clusters, among the largest gravitationally bound objects known, are not distributed randomly. Surveys of the universe reveal that they gather along filaments, immense strands of matter extending for tens or hundreds of millions of light-years. Filaments intersect at dense nodes where the richest clusters form. Between them lie broad sheets and walls of galaxies, while the regions between those structures contain far fewer galaxies. This arrangement is called the cosmic web. It is not a web made only of luminous matter. Most of its underlying mass is dark matter, which provides the gravitational framework into which gas falls and galaxies grow. The visible galaxies trace that framework, like lights placed along an invisible scaffold. In maps built from millions of observations, the universe resembles a branching network with dense knots, thin connections, and large empty regions. The pattern did not begin at full scale. In the early universe, matter was distributed with extraordinary smoothness, but not perfect uniformity. Tiny variations in density were present, preserved in the oldest light that can be observed. Regions with slightly more matter exerted slightly more gravity. Over billions of years, they drew in surrounding material, grew denser, and developed into the filaments, clusters, and galaxies seen later. Less dense regions lost matter to their surroundings and expanded into voids. Gravity amplified a faint initial texture until it became the largest architecture in the observable universe. The process was guided strongly by dark matter, because dark matter began gathering without being held back by radiation, in the same way ordinary matter was. Gas later fell into those dark matter concentrations, cooled in some regions, and formed the first stars and galaxies. What appears now as an immense network of luminous systems is therefore the mature form of very small early differences. The cosmic web turns emptiness into structure. Voids are not absolute vacuums, but they contain far fewer galaxies than filaments and clusters. Some span tens or even hundreds of millions of light-years from within a large void. The nearest rich concentrations of galaxies would lie across distances difficult to distinguish from absence. Yet voids are not irrelevant gaps between meaningful structures. Their expansion influences the shape and motion of the surrounding web. Matter flows away from their interiors and toward denser regions, sharpening walls and filaments over time. At the largest scales, a map of the universe is defined as much by what is missing as by what is present. The contrast between nodes and voids gives the cosmos its form. This also changes the meaning of being small. The Milky Way is immense relative to the solar system, but within a filament, it becomes one luminous grain among many. The local group is large enough to bind major galaxies together, yet it occupies only a small volume within Laniakea. Laniakea itself is only one region in the cosmic web, adjacent to other supercluster structures and separated by vast underdense spaces. No single level provides a final center. The solar system circles the Milky Way. The Milky Way moves with the local group. The local group participates in larger flows shaped by nearby concentrations of matter. Those concentrations belong to filaments that extend beyond any local definition of home. The hierarchy is not a stack of perfect nested spheres, but a network of overlapping gravitational relationships. Each step outward replaces a contained object with a broader pattern. At planetary scale, boundaries can be surfaces. At stellar scale, they can be gravitational domains. At galactic scale, they become halos and orbital associations. At the scale of the cosmic web, structure is recognized through statistics, motion, and density across distances so great that no observer can experience them directly. Light from one side of a supercluster may have begun traveling before complex life appeared on Earth. By the time it reaches a telescope, the structure has already changed. The map is always historical, assembled from signals of different ages. Yet the broad pattern remains measurable. Galaxies line up along filaments. Clusters gather at intersections. Voids open between them. The universe has an architecture, but it is an architecture made from growth, gravity, and time, rather than walls or edges. This architecture is among the largest patterns that matter has formed, and still, it does not occupy the whole observable cosmos as one singular structure. The web continues beyond the nearest surveys in every direction, repeating its broad statistical character across scales until the horizon of observation intervenes. The local group, once large enough to contain every galaxy that will ever merge with the Milky Way directly, becomes only one nearly invisible knot inside that web. The next reduction is therefore not from one object to a larger object, but from the cosmic web itself to the full observable volume in which all such structures are spread. The observable universe is not the same as the entire universe. It is the region from which light or other signals have had enough time to reach Earth since the cosmos became transparent, and its boundary is defined by time rather than by a physical wall. The universe is about 13.8 billion years old. Yet the observable region is far wider than 13.8 billion light-years in radius. This apparent contradiction disappears once expansion is included. While light travels toward Earth, the space through which it moves also stretches. The most distant matter visible today was much closer when its light began the journey, but that matter has continued receding as the universe expanded. Its present distance can therefore be far greater than the simple product of light speed and cosmic age. In the current cosmological picture, the observable universe is roughly 93 billion light-years across, with Earth located at the center only in the limited sense that observation extends outward from this location in every direction. There is no evidence that Earth marks a preferred cosmic position. This distinction is difficult because ordinary experience treats distance as something fixed between objects. In an expanding universe, distance itself changes with time. Galaxies are not generally flying through pre-existing emptiness away from one central explosion. On the largest scales, the space between widely separated galaxies grows. It is a change in the geometry of space. The observable horizon is simply the farthest region from which information has reached the present location. Beyond it may lie more universe, perhaps vastly more. But no current observation can reveal those regions directly because their signals have not had enough time to arrive, or may never arrive if expansion continues accelerating. The oldest light visible across the sky is the cosmic microwave background. It was released when the universe had cooled enough for electrons and atomic nuclei to combine into neutral atoms, allowing light to move freely instead of scattering constantly through hot plasma. Before that transition, the cosmos was opaque in much the same way that the interior of a star is opaque. The cosmic microwave background, therefore, forms a luminous limit to ordinary observation, not because nothing existed earlier, but because earlier light could not travel freely. Its faint radiation now arrives from every direction. Stretched by cosmic expansion into microwave wavelengths, small variations in its temperature preserve traces of the early density differences that later grew into galaxies, clusters, filaments, and voids. The entire cosmic web described nearby is rooted in patterns visible on this ancient surface. What now spans hundreds of millions of light-years began as extremely slight irregularities in a much younger universe. It shows that the universe was once hotter, denser, smoother, and far less structured. Every galaxy observed at later times belongs to the history that followed. Deep surveys turn that history into a layered record. A telescope looking farther away also looks farther back in time because light requires time to travel. Nearby galaxies are seen in relatively recent stages. More distant galaxies appear younger, at extreme distances. Astronomers observe systems as they existed when the universe was only a small fraction of its present age. These early galaxies can look compact, irregular, rich in gas, and active in star formation. Their light has been stretched toward redder wavelengths by expansion, requiring instruments sensitive to infrared radiation to study them. Each deep field assembles objects from different times into the same view. The sky is both a map of space and an archive arranged by distance. Estimates of how many galaxies exist within the observable universe depend on what qualifies as a galaxy and how many faint systems remain below direct detection. Early counts, based on deep images, suggested hundreds of billions. Later analyses indicated that the true number could be much larger if numerous small, faint galaxies are included. The total is not a settled census because most galaxies cannot be counted individually with current instruments. Astronomers infer their abundance by studying limited regions of sky, measuring luminosity distributions, and estimating how many systems fall below observational limits. Even a conservative count produces a population beyond ordinary comprehension. If each galaxy contained only a modest number of stars, the total stellar population would already be staggering. But many galaxies hold billions or hundreds of billions of stars, while the largest contain still more. The number of planets may be greater again, and the number of moons, asteroids, comets, and smaller bodies greater still. Human scale becomes impossible to represent directly. A person cannot picture every star individually because the mind cannot maintain such a collection as distinct objects. The numbers must be understood through structure, sampling, and comparison rather than imagination. Yet, even the enormous content of the observable universe does not fill it densely. Galaxies gather in filaments and clusters separated by voids. Within galaxies, stars remain far apart. Within planetary systems, worlds occupy tiny regions compared with their orbits. Matter repeatedly concentrates into islands, surrounded by much larger volumes of low density. The universe is vast not because every part is crowded, but because thin distributions extend across extraordinary distances. On the largest scales, ordinary matter forms only a small share of the total cosmic energy budget. Most matter appears to be dark matter, detected through gravity rather than light. A still larger component is attributed to dark energy, the name given to whatever drives the observed acceleration of cosmic expansion. These labels describe effects more securely than underlying substances. Dark matter helps explain how galaxies form and how clusters remain bound. Dark energy helps describe why distant galaxies recede in a pattern, showing that expansion has sped up over cosmic time. Together, they mean that stars, planets, gas, dust, living cells, oceans, and every familiar material structure make up only a minority of the universe. Most of its content is known through influence rather than ordinary visibility. Expansion also creates limits more severe than distance alone. Some galaxies observed today are already so far away that signals sent from Earth now will never reach them if the present expansion history continues. Their ancient light can arrive because it began traveling when they were closer. But the space between those galaxies and Earth has since grown in a way that can prevent any new signal from crossing the widening gap over immense future times. More galaxies may pass beyond practical visibility as their light becomes increasingly redshifted and faint. The observable horizon changes as light arrives from new regions and accelerating expansion carries others beyond contact. Local gravity will keep the Milky Way, Andromeda, and the rest of the bound local group together. But more distant groups may gradually disappear from view. Far future observers could inhabit a merged local galaxy surrounded by apparent darkness, with much of the evidence for cosmic expansion no longer accessible in the same way. The universe does not need to shrink for the visible portion to become emptier. The horizon can change while the whole continues expanding. This makes the present era unusual in a quiet sense. Observers can still detect the cosmic microwave background, measure distant supernovae, map the cosmic web, and see galaxies across a broad range of cosmic history. Still, every number attached to the observable cosmos remains a statement about access, not totality. Roughly 93 billion light-years describes the diameter of the region presently observable under the standard cosmological model. It does not identify the diameter of everything that exists. The full universe may extend far beyond the horizon. It may be finite on a scale much larger than observation can test, or it may be spatially infinite. Current measurements indicate that space is very close to geometrically flat on large scales. But near flatness does not by itself prove infinity. A surface can appear flat across a small region while curving over a much greater one, just as Earth appears flat across an ordinary landscape. The cosmic horizon may therefore enclose only a fraction of the whole, with no present method for determining how large that fraction is. This is the final spatial reduction. Earth is small beside the Sun. The Sun is modest among stars. The solar system is a point in the Milky Way. The Milky Way is one galaxy among an immense population, and that population occupies only the observable region defined by the reach of information. Beyond that reach, the universe may continue without any visible marker of where it ends, or whether an end exists at all. Physical smallness has now reached a limit where comparison becomes uncertain, because the largest frame available may itself be only a local window. What remains is not a larger object that can be placed beside humanity, but an unknown totality from which humanity receives only a finite horizon of light. Physical size has never been a reliable measure of significance. The observable universe contains structures so large that Earth disappears inside any honest representation of them, and the full universe may extend far beyond the visible horizon, perhaps without a boundary that can ever be reached or confirmed. Against that scale, a human body is negligible. A city is negligible. A civilization, viewed only as a concentration of mass, is almost nothing. Yet this final comparison introduces a distinction that the earlier ones did not. Mountains, planets, stars, galaxies, and cosmic filaments can all be ranked by physical dimensions, but meaning does not belong to the same system of measurement. A thought has no diameter in the ordinary sense. A memory cannot be weighed against a galaxy cluster. Understanding does not become less real, because the mind that carries it occupies a small volume of living tissue. The universe may contain objects whose mass exceeds that of the sun by billions of times. But mass alone does not produce awareness, curiosity, or the ability to reconstruct a distant past from faint light. The smallness of humanity is therefore exact in one sense and incomplete in another. It describes geometry. It does not settle value. This does not require placing human beings at the center of creation or claiming that consciousness is unique in all existence. No evidence supports such certainty. Life may have appeared elsewhere, perhaps many times, and intelligence may exist in forms that have never been detected. The point is more restrained. On at least one small planet, matter has developed the ability to examine the conditions that produced it. Atoms formed in earlier stars became part of oceans. Cells, bones, instruments, and nervous systems. Elements scattered through ancient stellar explosions entered the crust of Earth and eventually became components of organisms capable of studying stellar explosions. The same universe that dwarfs life has, in one known location, produced life, able to measure that disparity. This is not an escape from smallness. It is a consequence of it. Because every observation begins inside a local body, on a local world, under a local sky. Knowledge grows by extending outward from that limited position. The scale of the universe is not delivered all at once. It is inferred from parallax, redshift, orbital motion, background radiation, stellar spectra, gravitational lensing, and the changing brightness of distant objects. Each method converts a small signal into a larger structure of understanding. A star shifts slightly against a background. A galaxy stretches light toward redder wavelengths. A planet dims its star by a fraction. A microwave glow varies by tiny amounts across the sky. None of these observations is visually grand when first recorded. Their power comes from interpretation. Human beings do not overcome cosmic distance by becoming physically larger. They cross it conceptually, through measurements precise enough to preserve information carried by light over millions or billions of years. This creates a different kind of scale. A telescope may be small compared with a planet, yet it can gather photons emitted before Earth existed in its present form. A detector may occupy a room, yet it can register particles from the sun, ripples from merging black holes, or radiation released when the universe was young. A mathematical model may fit on a page, yet describe expansion across the observable cosmos. The contrast is not between insignificance and grandeur. It is between physical limitation and explanatory reach. The body remains local, while the mind constructs relationships far beyond local experience. Even so, the knowledge is never complete. The observable universe is bounded by the age of cosmic history and by the time required for information to travel. Regions beyond the horizon may exist without any way to influence present observation. If space continues far enough, there may be structures forever hidden, not merely because instruments are weak, but because no signal from them can arrive. The distinction between the observable universe and the whole universe is therefore a boundary on knowledge as well as sight. Science can describe what the evidence supports inside that horizon. It can test models against background radiation, galaxy distributions, element abundances, and expansion. It can place limits on curvature and estimate the age and composition of the visible cosmos. But it cannot turn absence of access into certainty about what lies beyond. The largest honest statement may be that the observable region is finite while the total remains unknown. That uncertainty is not failure. It is a precise description of where evidence ends. Human meaning becomes clearer within that limit. Meaning does not come from occupying a large fraction of space. If it did, emptiness would matter more than life, and giant stars would possess greater value than living worlds simply because they are wider. Size would make black holes more important than memory, and galaxy clusters more significant than every act of care, discovery, or preservation. Nothing in physics requires that conclusion. Physics describes mass, energy, motion, fields, interactions, and the evolution of systems. It does not assign moral worth by volume. The universe is indifferent to many human categories, but indifference is not the same as negation. Meaning can arise within relationships among conscious beings, even if the surrounding cosmos offers no external confirmation. A small event may matter completely to the lives shaped by it. A decision can alter generations while changing almost nothing in the mass distribution of Earth. A species can transform ecosystems while remaining invisible from the nearest star. Scale and consequence operate differently depending on the system being considered. At cosmic scale, humanity is negligible. At planetary scale, it is now a major geological and ecological force. At personal scale, a single life can contain an entire field of experience. None of these frames cancels the others. They answer different questions. The recognition of smallness can therefore lead in more than one direction. It can produce fear by removing the familiar sense of centrality. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. The Milky Way is not the center of the universe. And the observable universe may not be the whole. Every outward step strips away another imagined privilege. Yet, the same recognition can produce clarity. A civilization confined to one fragile atmosphere has practical reasons to protect it. A species with no reachable second home has reasons to treat its planet as rare, regardless of how many planets may exist elsewhere. Cosmic abundance does not make local survival automatic. Billions of galaxies do not provide another breathable world within reach. The vastness that diminishes Earth also isolates it. The larger the universe becomes, the more obvious the dependence on a thin biosphere around one small planet. This is not a sentimental conclusion. It follows from distance, energy, biology, and present technological limits. The nearest stars remain years away at the speed of light. The nearest potentially habitable worlds are not known to be inhabited or even truly habitable. No distant planet can replace the systems already functioning on Earth. Smallness, therefore, carries responsibility. The planet is physically minor, but operationally complete for every known form of life. Its oceans, atmosphere, climate, soils, and living networks cannot be exchanged for the promise of a larger universe. The cosmic perspective does not reduce Earth to worthlessness. It reveals how much value can be concentrated in a small place. The same is true of consciousness. The mind does not need to rival a star in size to contain a model of stellar evolution. It does not need to span a galaxy to infer the galaxy's rotation. It does not need to reach the cosmic horizon to understand why the horizon exists. Human knowledge remains partial, fragile, and corrigible, but its reach is extraordinary precisely because it begins from such a narrow base. A species that evolved to navigate landscapes and social groups now studies dark matter halos, exoplanet atmospheres, and the first light released into transparent space. That expansion of understanding does not make humanity physically larger. It makes smallness more accurately known. In the end, the universe does not become less immense because it is understood, and humanity does not become less small because it understands. The two truths remain together. Matter on one quiet planet has learned to measure distances that it cannot cross, timescales that it cannot survive, and structures that it can never see from outside. The achievement does not erase insignificance at cosmic scale. It gives that insignificance a witness. For now, in one known corner of one ordinary galaxy, the universe is not only expanding, cooling, forming stars, and gathering matter into structure. It is also being noticed. The universe remains larger than any image made of it, larger than any map, and perhaps larger than the entire region from which light can ever arrive. Its stars continue forming and fading. Galaxies drift through the cosmic web. Distant light crosses expanding space, carrying records of worlds and events that may have changed long before their signals reach Earth. Against that motion, humanity occupies a brief interval on a small planet near an ordinary star. Yet within that interval, the sky has become more than a ceiling of lights. It has become a history that can be read, a structure that can be measured, and a mystery given clearer edges through patient observation. Smallness remains. Nothing in knowledge changes the diameter of Earth or shortens the distance to the nearest star. No discovery moves the solar system closer to the galactic center or brings the cosmic horizon within reach. But understanding changes the character of that smallness. It replaces isolation with connection, showing that the atoms within living bodies were shaped by stars, that Earth belongs to a planetary system, that the sun moves through a galaxy, and that the galaxy follows the wider flow of matter across the universe. Every scale rests inside another, and every boundary opens onto a larger setting. The final picture is not one of insignificance alone. It is one of quiet participation. A small world turns beneath an old star. Oceans move beneath a thin atmosphere. Life continues within a narrow layer of warmth, carrying memories, questions, and the ability to notice what lies beyond. The universe does not pause for that awareness, yet awareness has appeared within it. For a little while, the immense structure is observed from one fragile point, and the darkness is not empty of meaning. It is simply deep, ancient, and still unfolding.